In this video, we will cover some basic mathematical tools which we will use for probability, statistics, and regression analysis. Those concepts are summation operators, linear functions, and natural logarithms. There is also a video on how to use the natural logarithms to display information in graphs, and also how to interpret that information. Okay, let us look at the summation operator. The summation operator is the large sigma sign, which is the Greek letter sigma, and we have a counter, which is the I. The 1 represents the starting value, and n represents the ending value. And xi represents the terms that we are going to sum up, and I is the counter. Okay? So for example, if we have the sum, if we have 3 values, then the starting value goes from 1 to 3. And if those values are demarked xi, then the summation operator is x1 plus x2 plus x3. Okay? So, for example, if we have x1 to be equal to 2, x2 is equal to negative 4, and x3 is equal to 5, and we sum them up, then we have I is equal 1 all the way to 3 of xi. So this leads to 2 plus negative 4 plus 5, and hence this is equal to 3. Now we will see that we can use the summation operator to make our definitions more efficient. So for example, if we are thinking about the definition of an average or the definition of a variance that we will see throughout this class, then using the summation operator is much more convenient. The natural logarithm is based on Euler's number. Euler's number is denoted with E. Think about Euler's number as a constant very similar to the number pi. E is defined using the factorial and also the summation operator. Note that 0 factorial is equal to 1. This is a universal definition. Let us look at 2 applications using the natural logarithm. Euler's number E has some interesting properties when it comes to interest rate calculations. Now, in the first example, suppose that you are putting $100 into a bank account and you get 3% interest rate on that $100. This means that next year you are going to have $103. Now, you can use the natural logarithm to calculate the percentage difference. So if you take the natural logarithm of 103 and subtract the natural logarithm of 100, then you get 2.956%, which is very close to the 3%. Note that the difference is more accurate the closer the two numbers are. So for example, the natural logarithm of 101 and you subtract the natural logarithm of 100 is going to be much closer to the 1% than if you are looking at a larger difference in numbers. So the percentage change in prices can be expressed as the natural logarithm of the price in time period 2 minus the natural logarithm of the price in time period 1, and that is equal to the interest rate. Now, the second example is about compounding interest rate. Now, this is, for example, if you have a car loan or if you have a mortgage, then because you are paying the mortgage or the car loan every month, the interest rate is compounded 12 times a year. Now, in this example, we are going to look at an interest rate which is compounded twice a year. Okay? So every 6 months. So if the interest rate is, again, 3%, then you have to take the 3% divided by 2. This is what we are doing here. And you have to then take it to the power of 2. So if the interest rate is compounded twice a year, and if that interest rate is 3%, then what you are paying over that year is actually $103.02, a little bit over 2 cents. Now, it turns out that here we have an example where the interest rate is compounded twice a year. As I said, when you're looking at the mortgage or when you're looking at the car loan, then the interest rate is compounded 12 times a year. Now, the question is what happens if that interest rate is compounded instantaneously? Now, in this case, you can see that the interest rate, if compounded instantaneously, if n goes to infinity, then the interest rate approaches Euler's number to the power of r. So the next concept that I would like to cover are linear functions. Linear functions is something we are going to see in the regression part of this class. But if you think back about high school and probably middle school, then you all know what a linear function is. A linear function is defined as mx plus b is equal to y, where m represents the slope and b represents the intercept. So when you're graphing a linear function, then you have x on the horizontal axis and you have y on the vertical axis. Then the intercept b is where the function cuts the axis. So this distance here is equal to b. And then assuming here that we have a positive slope. A positive slope means that if x increases, y increases as well. Then we have a linear function. And the slope indicates that if x increases by 1, then y increases by m, or by the slope parameter. Let us look at two functions using the concept that we have just learned. So for example 1, we have this linear function y is equal to 20 plus 5x. So what this means is that the intercept is 20, and that the slope is equal to 5. Note that this is a positive slope, so if x increases, so does y. So the function looks like this. So for example, if we have x being equal to 5, then we have 5 times 5 is 25, plus 20 is 45. So here, the function has a value of 45. Okay. Now, when we look at the second example, then here we have an intercept of 50, and the slope parameter is negative, with minus 2, which means that the intercept starts at 50. And since the slope is negative, this means if x gets bigger, y gets smaller. So the function looks like this. For example, if x is equal to 10, then we have 50 minus 2 times 10 is equal to 30. Okay. So this is how you use a linear function.